Hello, welcome to another PDP-11 video. I've done quite a few of them on these two computers, the PDP-1134 and the very similar 1104. But all I've done with them so far, with all those videos, is just muck around with the power supply and the interface to the console. And I've installed my interceptor thing that I used for my Easter egg hoax. That's in there now, so I can drive the console from a PC through this cable. But yeah, the next step of course is to get a working computer, and for that I'll need CPU boards, memory, I/O boards. So they're the next things to try out. I want to do everything in stages so that, you know, test one part at a time, make sure that works before sticking in something that depends on it. Now the CPU will depend on the memory. It won't be able to do much unless it's got working memory to fetch instructions from. But I believe that the memory can work standalone, or at least with this console, because this console is in fact a memory board. It contains the one location for the switch register, but it does a full unibus read-write operation to access it. So when you type in the address of the switch register here on the console and press the examine key, it actually sticks that address out onto the unibus, detects that that address is for itself, and then writes the contents of that switch register location onto the data bus, reads that back and displays it on the console. So it can do a full memory transaction. So I figure if I stick in a memory board, it'll be just like that, except there'll be a whole lot more memory locations to look at. And I don't think the memory board has any other dependencies. I thought maybe it might need clock signals or something from the unibus, or something that comes from the CPU to operate, but looking at the unibus signals, it doesn't seem to be any clock signals, so I think it should work. So here are the three memory boards I've got. These are M7847s. I've got three of them. Two of them are from the 1104 and one of them's Adless machine. And they're all complete. They've got the full 16K with parity, so there's 18 chips per row, 4K per row, so 16K there with parity. And the nomenclature for these things means that this is an MS11-JP. J means it's 16K, P means it's got the two columns of parity bits, I think, which is, you know, like there and there. Those chips fitted makes the parity. There's a couple of things that stand out. If you look at this board, you can, I think it's pretty visible. It's obviously been some heating going on there, and it's obvious on the back. And the others exhibit that as well to some degree. Hard to see, but there's a little bit of heating discoloration there. And the third one, yeah, also a little bit. Now, this one's got a dented regulator, bit of a worry. And these are all 4K by 1 memory chips, but they're three different types. Although I imagine they must be equivalent because everything else looks the same. To have a closer look at this overheated resistor business, let's have a look at the schematics for these things. This is looking at a photo of these things, and we can get a much better look at things this way. So there's the hot resistors, and there's a couple of Zener diodes there. Now if we look at the schematics, there's those two Zener diodes, and these are the resistors. 3 560 ohms in parallel. This is coming from minus 15 volts, and it provides minus 5 volts. In fact, two minus 5 volt supplies. One I think is for to do a battery backup, so they're separated for some reason. So there's two Zener diodes, 5.1 volts. One of them uses 3 560 ohms resistors, and the other uses just one 560 ohm resistor. Some memory chips, though none of the three types that I've got here, need -9 volts as one of their power supplies. These all use -5. So in the case of the -9, you would, according to this table down here, you would change this Zener to a 9.1 volt and change that resistor. But these ones are all -5, so they're both 5.1 volt Zeners. Why are they getting so hot? I actually did some calculations on the power requirements there. So here's my power supply, Zener power supply calculations. This is supply number 1's the one with just a single resistor and a Zener. We'll ignore the 9 volt option because we don't have that. -5 volt option. We've got -15 coming in, goes across a 560 ohm resistor to a 5.1 Zener. So the voltage across those resistors is 15 minus 5.1. The current through them is that voltage divided by 560, 18 milliamps, times 5.1 volts gives us 90 milliwatts dissipated in the Zener. And in the resistors, it's 18 milliamps times the voltage across them, 9.9, 175 milliwatts. The second supply with the three 560 ohm resistors, which comes out to 187 when they're in parallel, same calculations, 270 milliwatts dissipated in the Zener, 525 milliwatts in the three resistors, so that's 175 each. But that's not taking into account any current that's running out of the -5 volts, and that can be up to 325 microamps per chip, and there's 72 of them, so that can come to another 23.4 milliamps running through resistors, which gives us 3/4 of a watt being dissipated in the resistors and 250 milliwatts each. Now if they're quarter watt resistors, then they're sitting right on their limit. If they're half watt, then maybe they're okay, but I like derating resistors a lot more than half their rating because they still get hot even at half. So I think I'll stand them up or replace them with bigger resistors, something like that, just to get the heat off the board. We can see why it got hot. 3/4 of a watt, possibly. It wouldn't be hard, I guess, to put bigger resistors in there or stand them up off the board so they don't cause any more heating of the board. So I'll probably do something like that. The other thing that concerns me is these Zeners. If they let go, open up or burn out or something, then that -15 volts is going to go straight through to the chips. So instead of getting -5, they'll get -15, which can't be good for them, and they're all soldered in, so they'd be a mongrel of a thing to replace. So I'm thinking what I'll do is strap another Zener across each of those so that if this one fails, there's another Zener to support it. So yeah, I think I'll do that. I'll just solder another Zener across there, possibly do something about the resistors as well. And then of course there was that, this one's alright, but on one of those boards there was a dent in the regulator chip, which can't be helping. So yes, there's those issues. Now, while wondering if these boards could be plugged in standalone, not needing a CPU or anything, I figured, well, let's have a look at the schematic. These things are dynamic RAM, so they have to be refreshed. So there's got to be some sort of an oscillator in here to do the timing for that refresh, and because there's no incoming clock signal from the Unibus down here anywhere, so there's got to be an oscillator on board. So looking at the schematic for that, the usual pages of gibberish, layouts for all the different configurations of number of chips, some logic. This is basically plumbing for data lines, likewise there and there and there. And then we've got an orchard of chips, the RAM chips. There's a few pages of that. So the only place the oscillator can be is one of these two logic pages. Now this one is the address decoder. All the address lines go in there, and out pops address present. So that indicates that the address for this board has been selected. So that's not the oscillator. The oscillator's got to be on this page somewhere. And let's line that up a bit better. I could not see an oscillator in here. I thought maybe we've got a capacitor hanging off a logic line. often found in oscillators, and it looks like a loop there, but no, that is an input, not an output going back to this input, so it's not a loop. And in fact, there's quite a few of these capacitors hanging off logic lines. We've got them there, 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 there. So there's quite a number of them. They're mostly for pulse stretching and timing, as it turns out, just to get the things to line up just the way it's needed. Seems a bit hit and miss to me, but okay, I guess they know what they're doing. So I could not find an oscillator. I dug around in the maintenance manual that describes a bit more of the theory of how this thing works, and looking at that, you know, this simplified diagram of the refresh logic, and there you can see a loop around there. In fact, one of those signals that comes out of it is ref clock L. Let's see, and that's supposed to go active every 25 microseconds. And it's these capacitors here, C144 and 145, that control the timing of this refresh. So if we look at those on the schematic, there's those two capacitors there, and if we follow those, we get, it goes into there, which comes out as TC ref warn L. It comes in over here, goes through that to TC7 RFCV1, which goes to here and back down to those capacitors. So from the capacitors we go to here, 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 to the capacitors. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 gates, inverters and flip-flops in that loop. So yeah, I'm not surprised I didn't see a oscillator when I looked at that page, but there is one. So that means I should be able to plug one of these boards in and talk to it. Although, if you'd asked me a couple of months ago, will that work? I'd say, yeah, sure. There's no reason why these boards won't work. I don't doubt that these boards are okay to use. But given my recent luck with dynamic RAM on two 6809 systems, both of which seem to have problems, which I suspect is the RAM, I'm not so confident anymore. But I'll stick that board in and we'll turn on the power and see what happens, eh? Oh, we should look at the addressing. Before we do that, we should look at the addressing. That dip switch there controls where it appears in the memory space. So I'll review those and make sure that they're set to something sensible, and then I'll stick it in and we'll turn it on. Okay, there's the first board. That's actually one of the ones from the 1104, and it's set to address 0. The second one is set to address 16K, so that they're contiguous. And the third one is the one that came out of this machine. That's the one with the dented regulator. I'll leave him till last. But so this should give me memories, 16K of it, starting at location 0. First thing to do is just look for smoke. So here goes. Power supply on. Computer on. No smoke. That's good. Not yet anyway. And looking at the console, so we should be able to type in an address of 0, load address, type in a value, deposit, display address of 0, examine that location there. Okay, so let's go to, the deposit should have advanced the address counter. Start that again. Let's put in 11111, deposit, display address is 0. Should have advanced. I'll start again. Power off. Right. Load address. 111. Deposit. 222. Deposit. 333. Deposit. 4444. Deposit. 5555. Deposit. 6666. Deposit. 777. Deposit. clear, load address, now examine. 1, 2, 3, there's all the stuff I typed in, I think. This is just random gibberish, is it? Or is it memory errors? Load address, deposit. Deposit, 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 deposit. This should be filling memory with noughts. Display address, go back to 0, examine, or noughts. Until we get to where I didn't fill in anything. Good. So clear, let's try clear, load address. Value 17777, deposit, lots of depositing, and the top two bits aren't on, so it's not invalid as an address or data. Not sure what that bus is. We didn't get the bus error anyway. If we look at the address now, we've climbed up to there. Clear, load address, examine, and we get all those 17777s. So that's looking good. Bit more testing. Load address of 0, and I'll just put in 1, 2, 3, 4, 5, 6. Deposit, lots of depositing of that. Display address, we've got up to 150, so clear, load address, examine, 1, 2, 3, 4, 5, 6. Hey, I've got some dynamic memory that works. Bloody amazing. That's encouraging. Alright, I'm going to use this Bizzo that I can allow a PC to do what I'm just doing here on the console and make a memory test. So I'll have it go through and really test the memory by banging away at this keyboard via this cable and leave that running overnight and see what it comes up with. That's a bit later. Okay, this board's looking good. I'll try the other two memory boards. Okay, this is now the second board from the PDP-1104, and it's sitting at 16K address location, which is 100,000 octal. So I'll turn it on now. Again, look for smoke. No smoke. A little bus error. Now if I try and look at, if I load that address and try and examine it, I should get a bus error because there's no memory at location 0. But if I put in 100,000, load address and examine, no bus error. I'll do that again. 100,000, load address, and then put in 1, 2, 3, 4, 5, 6, deposit, do a whole lot of depositing. And the address got up to 1,060, 100,060. Clear, go to 100,000, load address, examine, there's our 1, 2, 3, 4, 5, 6, okay, that's looking good. And if I keep examining, we should run past where I entered the data, there we go, and we got Gibberachi. Good, that board's looking good as well. Now we'll try the third board, which is from the one that was in this machine. Alright, third board. Now this is the one with the dented regulator, so let's hope that doesn't cause a problem. Power on. This is back at location 0, so we can just load address of 0 and examine. Bus error. Ooh, not good. Load address. 1, 2, 3, 4, 5, 6. Deposit. Bus error. It's almost as if that board is not working. I have to check my addressing, but I believe it's at 0. Load address. 1, 2, 3, 4, 5, 6. Deposit. We're getting bus error. It's not responding. So that board's well, it might have to just flick, work those switches. They might be dirty or something, but there's something wrong with that one. So I'll turn it off and not do anything with him for a bit, just in case that regulator is causing problems. I really should be measuring the power supplies on each board to make sure that it's all good, especially the 12 volts on this one and the -5 on all of them with that Zener business. Yeah, this board, the one that originally came with this machine, still not working, the one with the dented regulator. I measured the voltages, I saw 12 volts here, -5 on the Zeners. I think its regulator's good, it was 11.8, but yeah. These switches are very dicky. I sprayed them with CRC, but yeah, they feel really floppy. So it could be that, but I've sprayed them to CRC and worked them backwards and forwards, and still doesn't work. So I like these slide switches a bit better. They seem a bit more positive. I'm getting a proper vacuum desoldering gun. It's on its way as we speak. I might try replacing that with a decent, better switch. But I don't need this board at the moment. In fact, I don't need it ever. I've got 2 working boards and I've got 2 computers that need it. So, but of course I'll try and fix it. But that definitely goes right to the back burner. So what I'll do now is try and come up with a automated testing thing using this interceptor gizmo. Okay, here's the beginning of my application to drive the PDP through that interceptor gizmo. Let's run it and connect. There we go, and then we can have a console. We can have it all sorts of sizes, but that's probably big enough. I'll just stick it over here. That's probably too big. That'll do. Maybe that one. Stick it over there, and we can send keystrokes, strings of keystrokes, like C stands for clear key, followed by 1, 2, 3, 4, 5. So we'll send that. Or a different sequence, and we can send W followed by a bunch of hex. Now W doesn't denote one of those keys there. It means write these hex values as segment glyphs, if you like. So we get that, and this is an attempt at a exclamation mark. It's as good as you can do with 7 segments, and Y just returns it back to normal display mode, so we get whatever was there before. We put that 1, 2, 3, 4, 5, 6 in there, and we can do dog or cat. Frog works out pretty well. Frog. Or we can go A dash, but if we go A dash, the asterisk isn't something that will print, because you can't print an asterisk with 7 segments anyway, so we do that, and it only overwrites the first 2. The asterisks mean leave the other digits the same, so we can type stuff into there. They're all in there, but we only see the last 4 of them. Okay, that might be useful for something. So let's get rid of that, go back to normal. And there's a crude beginning of a memory test. There's all that stuff we're just doing, we'll clear that. We'll test from memory location 0 for 16. And run that test now, and it just writes the address value at the location of that address. So the address, the data equals the address. So it's writing, for instance, location 7, it writes 7 in it. Then it goes back and reads them, and it should get the same values. So, good stuff. As you can see, it's not particularly slow. If we try and do fast, rather, it's not very fast. If we do 64 locations, it's probably going to get a bit boring, and it may fail. Now, I have been occasionally getting this bus error light coming on, and when that happens, it doesn't write to that location, obviously. I've slowed down the keystroke rate, so I haven't seen it since I've done that, so maybe that was all that was wrong. But there's something that has to be worked on. And 64 is hex, what? Sorry, octal. Octal 100, yeah. Octal 80, sorry. 88, yep. Yeah, that worked. Okay, now let's just try 16 again. But now I'll change the address where we store them. In fact, just to make it quick, we'll only do 8 and we'll start at location 100 this time. Decimal, which obviously is 144 in octal. Okay, and if we go to 2048, which is halfway into the first 4K. That works good. So now let's go to 4096, which is the start of the second 4K, so the second row of chips on the board. So far I've only been dealing with the first row. 4096. Which is 10,000 hex, octal. I'm so used to hex. So that worked good. Now we'll go to 8192, which is the start of the third block of chips. And if I go to 1, 2, 2, 8, 8. So that came back with a 1 where it should be a 0. And if I do the same thing in the fourth block of chips, starting at 12288 decimal, which is what, 30,000 octal. Same thing again, that bit there is on when it shouldn't be, and so it seems this whole half of the memory has that stuck bit, so that could be, well, it's unlikely to be two bad chips, isn't it? It's got to be a bad chip in the same position in both rows, so it's more likely, thank God, to be something outside of the block of RAM, but needs to be investigated. So we've now got one dud M7847 from the one from this machine. This first board from the PDP-11 is only half good, so let's try the second one from the 1104, the one starting at location 100,000. Now, unfortunately, these diagrams I've got are almost unreadable. Can't tell what the chips are there, and there are no chip designations on the board like there was with the M7859 console interface. That's got them, but this one doesn't, so it can be very hard to work out what chip is what. And from the diagrams, the diagrams for the memory arrays down below are almost as bad as this, so it's a bit hard to tell. But okay, we've got 4 banks there. These 2 banks worked, and in this group the 4th bit from the right, which may be that one, or it may be that one, but then I know that's parity there, so it's got to be, so it might be those 2, but whatever, it's the same bit in both the 3rd and the 4th banks, which means it's unlikely to be, you know, that chip and that chip failing, or that chip and that chip failing, whichever it is. It's more likely something to be that's common to both of these, but I've got to get better print set than what I've got. Hopefully, I know I didn't get any documentation with the 04, but I did get documentation with this, so I might have some originals of this engineering drawing set that I can be able to find out where the hell everything is, because this just doesn't help. Alright, so that one's dodgy. I've got the third board in there, or the second board rather, the second one from the 1104, the one at address 16,000. So let's fire up that test on this board. Okay, run and connect. And we'll do our little, does that still work, that trick? Yes. Okay, memory test, just for 16 locations starting from 0. Bus errors coming on a lot, that's not good. It's coming on every time. Of course, you idiot, it's at a different location. So we've got to start at where? At 16384, yeah? Yep, got rid of our bus errors, so maybe this is working. No, we've got an error there. But it wasn't in every location. Let's just run that again. Hope it's a perfie. Something to do with this way I'm driving this thing. Yeah. Oh no. Okay, we've still got a problem. Let's just try smaller groups though, just to test the various areas. There's obviously something wrong down there, but I'll worry about that later. Just want to test the 4 banks. Right, 8 locations works now. I can't do this in my head. 16384 plus 4096 is 2480. 20480. So this is the start of the second bank in this board that's at the second block. Still getting errors. So that one worked. Alright. So potentially there's not a problem. If I'm getting non-hard errors, I'm putting that down to just the way I'm interfacing this thing not being 100% for now. Now if we go to the next block, that's 24576. Just looking for hard errors at the moment. Soft errors, yeah, that could just be my dodgy software and hardware. That's obviously not a good one. 24576, yeah, that's right. Okay, got through that time, so that's our third block. and the fourth block in here is 28672. Error. Try it again, see if it's a hard error. No, soft error. So, there we go. Yeah. So all four banks in this, I'm getting bus errors here. So, but we're not getting the errors there. The bus error was flashing. It's a bit dodgy. Yeah, so early stuff. This interface, shut up. This interface is sketchy at the moment. I've still got some work to do. I know the firmware there's a lot of issues there to sort out. So at the moment, as long as it does that for 8 locations in each bank, I'm sort of saying to myself that those banks are okay. There's clearly 2 bad banks on that other board. I'm going to call this board good, and yeah, try and get the reliability of this interface up a bit, and the next step might be to actually plug in a CPU. But anyway, slowly making progress. I don't want to be spent doing 8 videos on bloody memory boards, but there might be one more in it. But I hope you found that enjoyable, interesting. Please like and perhaps subscribe if you find this stuff interesting, and I'll catch you later.